nice introduction. Thank you very much. Right, an invited tutorial. So, I've been asked to talk about theory of testing for process algebra, data-rich process algebras. But these days I'm very, very worried about software engineering for robotics. So I will follow my mandate and tell you a little bit about the work that we've been doing over the last 10 years perhaps with colleagues in New York, but also with Marie-Claude Godel from France, or Augusto Sampaio from Brazil, all contributed to the agenda of bringing a theory of testing to a refinement process algebra and its extensions, which is Csp. But before I get there, I'd like to tell you about the relevance of this work for the concern that we have today, which is the issue of software engineering for robotics. Robotics is, of course, a very fashionable topic these days, and I think it's for good reasons. They are evolving at an amazing pace. Results in mechanics, in electronics, in artificial intelligence means that the robots are much more interesting, they are much more interactive. We are seeing they are in the cusp of having these robots even more autonomous, coming to our houses, to public spaces and so on. So there is a lot of funding, there is a lot of concern from the safety community as well about what is coming our way. So, my group has embarked a couple of years ago on a 10-year program to address the issue of software engineering. So the vision that we have is that while from an electronics and mechanics point of view, robotics is extremely advanced, the software engineering approach is extremely primitive in this area, okay? So I'm going to talk to you today a bit more about this motivation that we have to talk about robotics, tell you what is the approach that we are following and that we are developing in New York with colleagues. That approach is based on a domain-specific language for robotics called RoboChart, which has a semantics that is based on Csp and its extensions. I'll explain to you why Csp is appropriate, and one of the reasons is why it's because it has a well-defined theory of testing. And I will tell you then what is this theory and how it has evolved over the years, giving you an overview of the work of my work and work of colleagues. And I will finalize it with an explanation of how we're dealing with the issue of mutation testing in the context of RoboChart. Okay? So it's a lot of material. I am going to be giving an overview of a lot of years of work. Please interrupt me if you think that I should be telling you more details or I need to be clear about anything. I'm very happy if I don't go all the way to the end, as long as you are with me all the way to the end, wherever we get, okay? But I see here actually a very, very senior audience. I call it a tutorial, I'm not sure. There is much I can teach you. Perhaps you will tell me how I can do better with my robots, okay? Right, so let me tell you what is my perceived current approach to the development of a robotic system. And that is based on conversations with colleagues in research laboratories developing state-of-the-art machines, but also with colleagues in industry working in small and medium companies, which is the majority of the companies working in this area have a small and medium profile. So the approach that they have is that they draw an abstract state machine to describe their design. But they told me that at first, and I said, oh good, they start well with a state machine. And I have here some examples of what they call state machines. A lot of English to start with, a lot of boxes, some of them overlapping over there, and we don't quite know what that overlapping means. Arrows that are not quite clear what they are doing and bifurcating, and then we have a flow chart there somewhere. I looked at that machine for half an hour and said, okay, I'll read the English, forget it. It's basically a drawing to guide and structure the English description, right? Here's another one. That is really not a model. That is definitely a drawing. There is no way I can handle that with tools. And you will see that there are some information here about time having elapsed and lost object for more than TA, whatever that means. And I thought, well, okay, so these are researchers in the electronics engineering department. They don't have that opportunity to have to be dealing with UML or SysML or whatever it is. I talked to colleagues in industry that they said, well, we actually use Word, and our engineers, they sit around the table with these Word drawings of state machines trying to find that lock, right? So we definitely can do better, right? But that's the state of the practice in many places. So that drawing, that's then used as a reference for them to establish what's the very first organized description of what the system should be. And that's the description comes in the form of a simulation or of a co-simulation. But that's the point where they describe precisely what their software should be, what the model of a particular robotic platform should be, and what a particular scenario or particular sets of scenarios should be to test the system under simulation conditions, okay? But what do they use? There is a variety of tools that are available for simulation. There is no standard, there is no platform independence. Once you choose one of these tools and you want to use another, you have to throw away what you wrote and write it again, because the API that is provided to deal with the platform or the environment is completely proprietary. The language for programming might be C++ or a proprietary language or C itself. So it is really low-level coding at the point in which they're still starting to think about the design of their models. That's what they're doing, okay? And then if they're lucky, their software, their simulator will generate some low-level code for deployment. And then at that stage, they face what is called the reality gap. The reality gap comes about because their model of the platform or their model of the environment is not faithful. They will say, for instance, that my floor is flat. And then when they put the actual robot on the floor it's, well, perhaps has some irregularities, it's not quite flat. And then they need to tune in their system. What does it mean? It means that they will be changing low-level code based on trial and error tests that they have guessed, they have generated by hand. No systematic approach to testing like this community would be able to provide. Okay, so it's really software engineering from back in the 70s, and there is a reason for that. There are first small and medium companies. Predominantly we have electronic engineers, we have mechanical engineers who are extremely skilled to carry out the tasks at their hands, but they have no computer science, they have no training in software engineering. Right? So that's the prospect, that's the current state of practice. So we then embarked on this program, a 10-year program, to define model-based engineering approach to developing these applications. So what is our stance? Is that we will start with a domain-specific language, we call it RoboChart. That language is based on state machines. You could think of it as a profile of the UML state machines, but it's enriched to deal with time, to deal with probability. So it's a subset of UML in a respect, but it's enriched with time, it's enriched with probability in another way as well. But it's a state machine notation that we can convince our colleagues in robotics to use, okay? So with the idea, of course, we have a well-defined syntax, and we have a semantics as well, based on Csp and its extensions. So this language exists. It's been developed on this 5-year EPSRC project. We have a tool. I will mention the tool briefly in a little while, and you can use it and see examples and so on. And the idea of this tool is that I will never ever have a chance of convincing a roboticist to write a Csp model of anything, right? They can't even read it. That's the truth of it. Okay, and I don't think Csp is that mysterious and at all. I think it's a readable language. It's a language that has animators. It's a programming language. It looks very much like a programming language. I can teach it to my students, and they feel that it's easier than Z, for instance. But I won't convince my colleagues in robotics to write it. So we have automatic generation of what I call proof model there, of a Csp description of the system. which I then can input to model checkers and theorem provers. We have been working, of course, with FDR, with Isabel. We can generate as well models in reactive modules to work with Prism. And I'm looking in this program, this 10-year program, for colleagues to join me and say, okay, but I have perhaps a different alternative that I could have, that I could use to give semantics to RoboChart, and I'd like to try, how can RoboChart be a front end for my technique? If you are interested in doing that, I welcome very much. But the only point that I would make, yes, but let's make sure that whatever new technique we bring to the pot, you can justify by saying that the mathematical meaning that's behind in that technique is compatible with the other ones that exist. So that every verification, every testing technique, every proof that we can write, we can say, okay, that is true in every model that we have written. There is a unified view of what a model is. But well, for those, of course, we need properties of interest. And if I go and use something cheap, model checker or tactic of proof that can tell, for instance, that my model is deterministic as I expect, or it's deadlock free and so on, if it's valid, very well. But if it's not valid, I will not ask colleagues to go back and work with the proof model. We go back to the RoboChart model, fix it, and go and try and prove it again, because the proof model is hidden from the practitioners. And because this line here is all automatic, that's very cheap to achieve. If it is valid, we want to automatically generate a simulation model. And I'm calling it a simulation model because I want to generate another diagrammatic description of the simulation, not code in C++ yet. I will still want to have a high-level description, two independent description of the simulation. But from that, I want to generate, and we can generate, code for robotic simulators. We can cope with 2 at the moment. And using that robotic simulators, we can again ask, is my design valid? Are extra properties that I found it easier to establish using simulation valid? If they're not, I should go back to the diagrammatic models. Never, ever again look at a line of C++ code. That's my ambition. Okay? If it is valid, however, I can automatically generate a code for deployment. And we will ask me in this audience, I'm sure, what about the tests? Well, we can, of course, use RoboChart models and RoboSim models as well to generate tests. And there will be tests. We have already started this work, and I'll tell you a little bit about what we already started. This project started less than a year ago. We can, of course, generate tests from a RoboChart model, and we have tests for use with simulation and tests that are converted to use with the system itself. So this community, I think I don't need to explain that they need to be different due to observability issues. And the idea is that from these tests, you can ask, is my system finally correct? If it's not, go back to the models. If it is, I have provided not only the code, but also a whole load of other artifacts that I can use to establish certification of any claim of quality of my system. So that's where we're trying to get in this 10-year program. And I will start next telling you more about RoboChart and about how RoboChart is being used to generate test cases based on the theory of testing that is given by Csp and its extensions that is underpinning RoboChart. Question?
I see a lot of green arrows, and you said that it's automatic generation, so what are you testing here? Are you testing the compiler?
No. Right. Okay, good question. Let me explain. So here, I am automatically generating a simulation, right? And I get the robotic simulator, and how am I going to use it? How am I going to use that simulation? What I know, right, if I write a simulation by hand, what I may have done is that I have created a model of a simulation of the state machine that is incorrect. So if I look at the simulation and I see that the simulation offers a behavior that is inadequate, I may have made a programming mistake in generating the simulation. Okay? That is not going to happen. Okay? But my design may be wrong. The simulation will be a correct embodiment, a correct encoding of the model that I wrote. But is the model that I have valid? Is that robot? The problem with the robotic system is I don't know what the right specification is from the beginning.
I'm wondering, because the test cases are generated from the same model.
The test cases are generated from the same model, but they are generated to define what's the environment. I'm not going to find the assumption that we have here is that this model here may not be valid. Yeah. The software controller that I am providing, it may not be the software controller that's right for that platform and that environment. So when I generate the test cases, I will be exercising the simulation to tell me, in this environment with this platform, is this software controller adequate? The question is not whether the software is correct, is whether it's not whether the simulation is a correct embodiment of the design, but whether that simulation is itself a correct design.
So the round thing you have robo in and robo chart. Okay. In a sense, the way I see that is that you have something for your actual system that you're interested in, the robot itself, and then the environment is different kind of test cases where you're trying to test two different scenarios in the environment. So it's only a part of this that you're actually generating or
yes, it is. For now it is. Okay. For now it is. But it's also the issue of it doesn't matter using those tests to exercise that model. Even if the tests were generated from the same model, I know I'm using the simulation to exercise that model and reveal what is the behavior. It may not be because of the way the platform behaves, because of the environment that you actually define. It may not be that that is the right software, even though you have coded it correctly. Oops, sorry, I should be using that. Even though I have encoded it correctly, it is not the right model. So that's the issue. Have I answered the question? Yeah. 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 Is that clear? Okay. So one thing that colleagues in robotics may do is to use evolution algorithms to generate the simulations and find values for their control parameters, for instance. And so that is another way in which they can use control parameters, okay? Or find out that they forgot something, for example, okay? It's a validation of their model. I think that's an explanation, okay? All right, so going forward, RoboChart. So RoboChart, as I said, it's a constrained version of UML state machines, but enriched with time and probability. I'm not going to cover the work on probability here, but I will illustrate the use of time modeling facilities that we have. We have a customized component model. We have state machines with component diagrams as well, but the component diagrams are very much constrained to establish the needs of robotics applications. A number of well-formed conditions, much more restricted than you would have in UML, for instance. And a formal semantics based on Csp, so a process algebraic semantics for refinement to include untimed, timed, and probabilistic versions of the system. We have tool support, as I explained. The tool support for creation and validation of the models. To my surprise, people say that most of the modeling tools that are out there don't support validation of obvious well-formedness conditions of diagrams. We do. And code generation, in the sense that we're generating formal semantics automatically, and also the simulation. So here's a little example, very small example, of a foraging robot that is developed by colleagues in electronics engineering, and it's part of a swarm of robots that are inspired by ants that are foraging, and they have an idea of a source area where they collect objects, and then they collaborate to take these objects back to a nest, and they collaborate by passing to each other the object to go forward, so that they cover just a small area of the path that they need to follow from the source to the nest. So that's the example I'm going to give. And that's the example. It starts here. This is a module called Foraging. So that large block there is a module, which is a representation of a robotic system. And a module that specifies a single robot, not the whole swarm. It is characterized by a robotic platform. The robotic platform here describes just the services that you expect that your platform will provide for you, either by hardware, by sensors and actuators, or perhaps by a library that comes, an API that comes with your platform providing facilities. The behavior of the system of the controller software that you want to specify is specified by one or more controllers. So in my example here, the robotic platform is here, Foraging RP. It's a reference to another block that specifies the platform, and I will show it to you in the next slides. And it has two controllers, obstacle avoidance and foraging C. Communication between the platform and the controllers is always asynchronous. That's how it is in robotic systems. Communication between the controllers may be synchronous or asynchronous. And that's these communications, they characterize events. The robotic platform, as I said, provides a description of the service. So we have an idea in RoboChart of what is a data model, where we have variables, events, and operations that provide an abstraction of the sensors and actuators and whatever API you have in your robotic platform. So the idea that you have is, I am going to program this software, and these are the services that I need to actually get it programmed, but it may be realized by a variety of different platforms. So if for a simpler example, if you have a vacuum cleaner, for instance, then we will have the software, the high-level design of the software that you're going to implement in this vacuum cleaner will require operations to move, obstacle detectors, and there can be several different platforms that implement that kind of functionality in various different ways. So the data model provides this separation of concerns, makes the actual platform or the decision about the platform in a simulation. You have to be very concrete, but here you can be abstract and say my controller and my state machines, they are independent of the particular platform model that I use in a simulation, and provide a single point of interaction with the robot. So here's the example. The example that I had was a reference to this block here, which is the platform for the Foraging Robot. And this platform, it provides two interfaces. So we have an idea of interface. I'll look first at this interface here for movement, where we say, well, this robot here, it has two variables, LV and AV, which is the linear and the angular velocity of the robot, which representing basically an actuator, something that I can change about my robot to define its speed and direction. It also has other operations. It has an API to control movement. I can change the values of LV and AV by an operation move. I have an operation to explore the area of the source, explore the neighborhood wherever I am, to go to a particular position. I have other operations to grasp and to transfer objects and so on. All these are low-level operations or control operations that I say, these are, I take them as given. I am not interested in testing or modeling them. They are assumed to be all right. If that is not a good assumption, it means then that I don't put them there as being provided by the platform. They will be part of my controller software. So that's in the sense the robotic platform is defining the scope of my system. And finally, I have some events here: transferred, collect, obstacle, and stored. Obstacle is clearly abstracting away from a sensor that will verify, that will check whether I have an obstacle on my way. Stored will tell me if I manage to store the object in the nest as the robot is expected to do. So this is the robotic platform. As I mentioned, we have two controllers. Here's an example of one of the controllers, Foraging. The controller, describes as well the variables, events, operations that it uses. Each component is a closed component. We can analyze each component individually and compositionally. its behavior is given by state machines. So a system is composed of controllers running in parallel. A controller itself may have its behavior described by a collection of state machines, either to just separate functionality or to specify parallel threads of computation. Communication between state machines is synchronous, just as a question of abstraction. So, state machines, I won't spend much time telling you about state machines. I'll give you an example just basically to illustrate what is it that we have that's not in UML, which is basically the time facilities. But also I'll make just a quick note that we have, it is of course the main behavioral construct of RoboChart that we use to model both operations and the behaviors of controllers, as I just said. We have all the expected facilities of simple composite final states, transitions, but no interlevel transitions to avoid issues of compositionality. We restricted the language to have a semantics that is tractable, basically. And here's one of the state machines, which is in a more readable way here. I hope you can read with this size. The machine, again, it declares the variables, operations, and events that it uses. The events are over there. Again, because at the level of machine, I also have full encapsulation, and I can deal with each machine individually. And we will see that in our example for testing, that's what we are doing at this stage. So here's my machine. It has an initial state exploring, where during that state, the operation explore is called for the robot to explore the source where it will find the objects. Once an object is collected, that event is raised, then the robot goes to the state go to nest, where it initializes a variable dist, which is with the value 0, and then it goes to the nest, or attempts to go to the nest. So if, for example, the distance that it's traveled is greater than p, then it thinks, oh, okay, I'm very far from the nest. It's time for me to try and transfer it to another object. So if distance is greater than p, it goes to the state wait for transfer. And in wait for transfer, it will reset a clock, call the operation transfer, and it will wait until the event transferred has happened, which represents a successful downloading of the object to another robot. However, if that clock has exceeded a value called a wait deadline, then it says, okay, there is nobody to relieve me from this object, I'll go to the nest directly. So we have time primitives in terms of clocks. We also have budgets via waits. We also have deadlines. And for that reason, of course, we need a semantics on Csp that takes into account time as well. So that's my very brief overview of RoboChart for you. Semantics is being given, as I said, in Csp. Why Csp? Why choose this is a semantics language for RoboChart? For two main reasons, and they are highlighted there in red. The first reason is that it's a language for refinement, and that I need the notion of refinement to establish that the RoboSim, that the simulation model, is a correct implementation of my RoboChart model. So that is important for that flow of work that I have there. So of course that's why I established the notation for validation and verification. There are many others, but refinement is a central point here. It is well established in the sense it has the notation, operation, and algebraic semantics, certainly for the core language, can deal very well with reactive concurrent systems, but most of all, it's extensible. We will be able to take, or we are taking advantage of extensions of Csp to deal with complex data types. So we have worked over the years with a notation called circus that combines Z and Csp, has a very rich data model, and that's the actual model of a full RoboChart model. We will use rich data types as roboticists would need, and we can cope with that. Of course, we need to deal with time. We need to, and that can be done with a dialect of Csp, and we support that dialect, and we support it with a very strong denotational semantics that we have developed just recently, all because we have the UTP, the Unified Theories of Program, behind the scenes, and the possibility via the unifying theories of programming of encoding the semantics not only in a model checker in FDR, but also in a theorem prover. And our group has been using Isabelle, and you might have seen some talks this week about Isabelle UTP. And on top of Isabelle UTP, we can write models of our RoboChart descriptions, and those models may include probability. Those models may also include the continuous models for the platform and the environment. So CSP, in that sense, it's almost a front end, and there's an easy route for early validation of the models. Our overall target is to have this comprehensive semantics catering for all these aspects, and we are confident that we can do it because CSP has these unifying theories of programming semantics. Okay? So that's why CSP. I thought I needed to introduce CSP to the audience that I was expecting. Do I? Does anybody here not know what CSP is?
Knowing and knowing.
There's knowing and knowing. Okay, right. So I'll be very quick, and anybody who doesn't understand me, stop me. Deal? Okay? So CSP process algebra means that a system and its components, they are specified by processes that interact with the environment via events. So events in CSP, they are different from the events of RoboChart, and we will see the difference in a minute. Events are atomic instantaneous synchronization points, and I've given here a very simple example. This is not at all the semantics of the machine that I just generated, but I put here a very simple example in CSP that I can use to give you examples of the tests and so on. So in this very simple DTP, the robot is first ready to collect the object, and so the event collected marks that interaction, and then it behaves like the process store offers an external choice to the environment, saying, well, either we have an input to say that, either we have an indication that it's stored or an indication that I am too far. And if I have an indication that it's stored or that it is too far, I decide on the choice. If it's stored, I behave like simple DTP again. If it's too far, I behave like the process transfer until it's actually transferred, and I go back to behave like simple DTP. So CSP offers the notion of external choice, also the notion of internal choice, where the process we have an internal choice is capturing non-determinism. The process itself makes its decision, has very powerful operators for parallelism, for encapsulation via hiding, renaming, and so on. It is the language that I said that I will use. And in RoboChart, when I give the semantics of RoboChart, the question that we ask in the CSP process that capturing the semantics of a RoboChart, what are the visible events? What are the CSP events that corresponds to a RoboChart model? And that will be based on the robotic platform. So that's one thing about an embedded system, in the robotic system in particular. You don't see we don't interact with the software. You interact with the robotic platform that is running the software. So what is visible in my system? It is those services that the robotic platform provides. So I can see the variables of the platform being updated, the events of the platform happening, and the operations of the platform being called. So these define the events of the underlying CSP process. Here's an overview of the semantics. Don't worry, I'm not going to be giving you detailed CSP process. It's, as far as we're concerned in our approach, that's assembly code, that's automatically generated. Just want to give you an overview that it's actually very compositional and very, I think one of my assistants would not be very grateful if I called it simple, but I think the structure is very elegant, and in that sense I think it's simple. They have managed to say, okay, a module is captured by a CSP process. It's the robotic system defines a process. It's a process on this event, oops, sorry, back to go back. It's a process whose events capture these variables, events, and operation calls of the platform. And that's defined just as the parallel composition of the behavior of the controllers, with the connections defined what are the synchronization sets, how do the parallel process synchronize. So if there are communications that are asynchronous, we model buffers in CSP. When you look at the controller, The controller is also defined by a Csp process that's used in the parallel composition to define the module. And elegantly again, the definition of the semantics of a controller is the parallel composition of the semantics of state machines. And again, the connections are defined the synchronization sets. And finally, we have the semantics of the state machines, and that's also a process. And again, we try to make the whole system, the whole semantics compositional. For instance, the state machine is defined by the parallel compositions of the semantics of states. And you might seem to think that's a step too far. Why would I want to analyze a state by itself? A state can be a composite state. A state can have a state machine in itself. It can be, for instance, simulated separately. And in one of our collaborators has that view that a composite state would be an isolated component of a simulation in his tool. So it's a parallel composition of states, and with the treatment of transitions, junctions, and so on, all embedded as part of the semantics of each of these states. Okay? So I think that's all you need to know about to understand what we are going to be doing later in terms of generating tests by mutation. The next thing I wanted to tell you is about Robo2. Robo2 exists. It's an academic tool, no doubt, right? But it is a usable tool. We have had very good feedback from colleagues using it. So if you are interested, you go into the RoboStar page, which is the page of my research group, and you can download Robo2. Robo2 accepts RoboChart models and a description of requirements. That's a point where I need to carry out some further work. We have 9 years ahead of us, so we'll get there. But the idea is that eventually those requirements, the properties of interest, they will be specified in a way that is amenable to roboticists as well. We would like to have a controlled natural language. We have a very modest natural language at the moment where in Robo2 you can write a file to tell what it is that you want to specify, and you can say check that such a process is deterministic, check that such a process has this trace, and all that in English, so that my colleagues in electronics don't need to learn Csp. But we need to do much more than that. We would like to have sequence diagrams. We'd like to have annotated sequence diagrams to deal with refinement assertions, but also with LTL properties for prism and so on. But with these in Robo2, Robo2 can generate Csp and timed Csp or stock Csp for use with FDR and Isabelle, and can generate reactive modules for use with Prism and Storm. Reactive modules is language accepted by several tools. We can generate C++ as well for use with a simulator called Argos, but also more recently as well, I need to update that figure, we also using VREP, which is a more widely used simulator for robotics. Argos is quite special. It can deal with any application, but it is targeted to swarm applications. So we can generate the simulations as well. So the tool is there. There are several case studies. Yes.
People want like that?
Oops.
So are you only intending to be standalone simulations, or could you imagine that you could generate code that could be, or forming a simulation unit that could be used with other things, such that you could have a more realistic thing of the actual dynamics of the robot? So.
Right. Okay. So that's a part of the project that I'm not covering here. RoboSim, not RoboChart, and I'll explain why, but RoboSim also has, besides so remember that from the first diagram, we had RoboChart as the design language, and we had a diagrammatic language for simulation as well called RoboSim. RoboSim has a idea of a state machine. The paradigm is different because it's the paradigm of simulation. Events are variables, for instance, but it has facilities to model the software, but also has facility, a diagrammatic language based on block diagrams to specify the physical model, okay? So that diagrammatic language, it exists already, we are implementing it now. It allows us to define what we call the P models and the physical models. And those models, they describe links, junctions, sensors and actuators. And sensors and actuators and the joints, they have their behavior specified by systems of differential algebraic equations. And our idea is that there will be two things going on there, three things going on there. One is translating from these physical models to SDF. SDF is an XML-based a language that is accepted by reactive simulators. That's one thing. The other thing is that we will generate CSP, hybrid CSP models for use in Isabel. The other thing is that I will convince some student in the future to use co-simulation tools so that we can pick up the physical model and describe it in Simulink, and you can have a RoboSim realization of the model in Simulink. I already have colleagues in Brazil translating the RoboSim to state flow in Simulink, and I'd like it to be translate the physical model to Simulink itself. But I'd love to use your co-simulation tools as well. Okay.
On which level do you plan to apply it? Because in robotics, I mean, you have the AI level where the reasoning is going on, planning, for example. Then you have the lower drivers or components of this, like the planner itself could be a development. So because, for example, prison, I think you propose it here for verification, but actually it's also synthesizing the plan as a scheduler strategy where to move. This is also part of the process where, I mean, my colleagues will say, okay, the robot should go to A and place A, and then it creates a plan where to go. And so where is this planning and this reasoning?
Okay, Jim wants to say something. Is that right, or is it another question, or shall I?
No, it's not another question, it's answering his question.
Okay.
So I'm doing some of that work, indeed planning advice. You do planning with resources, not stated resources using Prism. It's a powerful thing. You could also do probabilistic planning, because you want to trade off the accuracy of the plan against the time required to actually develop the plan. So all this will go on there.
So you will also use Prism not just for verification, but also during for planning, for example, for intelligence.
And it might be stored as well.
Absolutely.
You play a game basically, yeah? It's a fantastic game.
When Jim starts doing that, we will need to adapt that figure that I told you at the beginning. Let me give an answer now that is perhaps will tell the others how it fits in that picture of the beginning. What you're talking about there, that systems they have the part of planning, you're talking about the usual layered architecture of a robotics application. And you have a part of planning that could be a planner that I can understand, or it could be a deep neural network. There could be aspects there of computer vision. One of our applications is a chemical detector where a component that is there is a component that can accept the gas that the nose analyze the gas that the nose is detecting and use some very complex algorithm to detect which kind of gas is that, is it harmful or not. So all these things, they are not in the scope of RoboChart in terms of I'm not going to model computer vision algorithm, I'm not going to model deep neural networks, I'm not doing that. What we are working with RoboChart at the moment, and I don't have an answer to give you now, is that component model that I showed you does not embed the level of layers. And the question that we're answering at the moment is, how do I model layers using that component model? Do I need to extend RoboChart, or is there a design architectural pattern that I can use to capture those layers? That's something that we are going to investigate. But at the moment, when I have a component like the nose, or I have a component that is a deep neural network, all we do is to say this is a black box, which I understand absolutely it cannot be the final answer. And Jim will be doing some work. We have a student just starting to help us to learn about the models and the work that you've been doing, that Alessandro has showed here this week that I had the opportunity to watch. They are very interesting and relevant, right? But what we are working at the moment in RoboChart is you have the planning layer, you have the executive layer, you have the functional layer. We certainly can cope with the executive and the functional layer, right? And those are important too. Okay? But yeah, there's so much work to do.
They also use this robotic operating system, ROS, which is really a complete framework.
If you want to have a safety critical application, you don't, right? Yeah, if you want to have a safety critical application, you're not going to use ROS, right? If it's real time critical, you're not going to do that. But I know that that's what people are doing, right? So I had some enthusiastic students modeling ROS applications as well, and I let them enthusiasm, and it's good. But yeah, okay. All right, any more questions? Okay, so going on. Right, so as I said, many case studies. Now, get into what this community perhaps will find either interesting or too easy, I don't know. But the testing from CSP, years ago, I think 10 years ago, Marie-Claude Godel and I defined a testing theory for CSP. It is a fully fledged testing theory, formal testing theory in the sense of Marie-Claude's formal testing, right? And also that testing theory has been, along the years, together with Marie-Claude and other colleagues, we have extended it to deal with symbolic testing for circuits, for our combination of CSP and Z, to deal with inputs and outputs. One thing I haven't told you is that CSP does not really distinguish whether an event is an input or an output. And of course, for the testing community, that is shocking. We have addressed that, and I'll tell you a little bit about it as well. Another one is the relationship between refinement and IOCO. And I know that IOCO is a very successful conformance relation, and it's very appropriate for the use of testing. A lot of respect for IOCO, and what we cannot have is people going to the labs trying to generate code that's correct with respect to refinement, and then giving it to testers that are going to use a different conformance relation and come back and say it's wrong because they used a different conformance relation. So we have been looking at the relationship, and I know that Bernard has made some contributions there that we took advantage of what is the relationship between refinement and IOCO? What do we need to do to make sure that this unfortunate situation does not happen? And we have also worked on selection strategies for CSP. But it's another reason why CSP is an appropriate notation for us to underpin our technology. It's because we can deal with testing as well. Okay, so what I'm going to do now is to tell you what the components of the testing theory for CSP and look like when what the components of a testing theory look like when they are instantiated for CSP. The first thing that Marie-Claude and I have done is that we said, okay, we are in a very fortunate situation here because most of the testing theories, I think all the testing theories that Marie-Claude had worked with before, they were based on operational semantics. We could base our work for CSP on the denotational semantics because there is a very clear relationship between the denotational and the operational. All the operational concepts that are usually cast in an operational semantics, they are available at the level of the denotational semantics, and there is a proof, a mathematical proof that they are isomorphic. So we could work with the denotational semantics. Denotational semantics for CSP, there are several, and that's been our challenge over the years and our fun over the years as well. Of course, the simplest model is the traces model. The traces model, for my very simple example, the traces of a process, the set of traces of a process, of course, it's in general infinite. The traces are prefix closed, that's the nature of the semantics of CSP. So if I look for my simple example, simple DTP, it has, of course, the empty trace. It's a trace of every process. We have the trace that only has the first event collected there, or you have collected followed by stored, or collect followed by too far. It's a very simple model. The problem of this model is that it cannot distinguish between what is external choice and internal choice. This is a concept that's more of CSP than of finite state machines, of automata in any way. But we need to have, if we want to distinguish between external choice and abstraction, which is the non-deterministic choice, we need to deal with the failures model. The failures model is a model that after each trace, you record refusals. What are the events that can be refused by the process? If the process is executed in an environment where only those events are provided, can that process can refuse to progress, it can deadlock. So I can give you the example here. So for instance, at the right beginning, this process will only accept the event collected. So if it is in an environment that's offering stored, too far, or transferred, I have a deadlock. And of course, if the environment offers these three and the process can deadlock, of course, if the environment offers even less, it will deadlock as well. So the refusals are subset closed. After the event collected happens, then we have an external choice. The process will agree to offer stored or too far. So after the event collected, if we have the environment saying collected or transferred, then I have the possibility that I have a deadlock as well. And on it goes. After collected or stored, it goes back to behave like simple DTP. So I have again the same refusal and so on. So these are two of what is called the canonical models of Csp. The real canonical model is the failures divergences model, where besides the failures, we record as well the divergences, the traces that lead to a divergent, to a live-locked behavior in the process, where it is engaging in an infinite number of internal actions and doesn't ever come back for interaction. However, as I understand in this community, the assumption that's made is that systems are divergence-free. When you observe a system that's divergent, you cannot distinguish it from a system that's deadlocked. You consider that specifications that have divergence that are just invalid. And so we say specifications mistake at the system level, at the system on the test level, it's a deadlock. So the assumption is divergence-free. With that assumption, the failures divergences model just is isomorphic to the failures model, and that's what we use. However, as I mentioned already, we considered other models later. We consider input-output failures to be able to distinguish inputs from outputs. We will see that that is not satisfactory from the point of view of having refinement and IOCO in the same sort of development approach. And then we go on and deal with refusal traces. And at the moment, we are developing a testing theory for what we call TikTok, which is the notational model that can cope with time, a discrete time in Csp, where you have termination, non-determinism, Zeno behavior, and time locks are used to specify deadlines. So a very rich model that we have developed now called TikTok. We are developing a testing theory for it as well. So, conformance, then the interest of our work was that conformance was an unusual relation for the testing community, as I was told, which is the refinement. So we had trace refinement, is the simplest notion of conformance in Csp, which is restrictive on traces. So basically a process P is refined by a process Q if every trace of Q is a trace of P, and that of course is all right for safety, but the very best process in that case is a process that does nothing. The only trace is the empty trace. So it is a restrictive notion of conformance, but it deals with safety. There is nothing that it does that is not predicted in my model. The other one, which is canonical for divergence-free process, would be the failures divergences that requires that every failure of Q is a failure of P. And that is still restrictive on traces, but prescriptive on acceptances. So basically, Q can only present a deadlock if P allows that deadlock to happen. Okay? So these are the things that are important. And one common feature of every model that we studied in Csp so far is that refinement is always subset containment. And so the ideas that we have used in this core testing theory, they are being surviving the test of more complex models because of this uniformity of the notion of what refinement is. Another ingredient of a testing theory is the testability hypothesis. And the testability hypotheses are pretty standard, but of course Csp has its own peculiarities. The standard hypothesis that we make is that the SUT behaves like some unknown Csp process, right? What does that mean? You need to understand what's the paradigm that is embedded in Csp, and basically that the events that you use to write a model, they are atomic and of irrelevant duration. And for that, there is no formal argument that you're going to make. You can have complementary tests or proofs. Is my model appropriate? Is it made assumptions? Is it capturing what an interaction is in an appropriate way? The events are really instantaneous of irrelevant duration. Complete testing assumption as well, because the systems can be non-deterministic. I think this community is also very familiar with that. There is some known integer k such that if I perform k experiments of a test, I can be sure that every behavior of that system will have been exhibited, and I am not going to be tricked by saying, that was not covered by my testing. So that can only be enforced by empirical knowledge of the system. We have the notion of test execution, and the notion of testing execution on a testing theory is very important because it's the basis for you to prove properties about your sets of tests. And in the case of Csp, we have this standard idea that test execution is the parallel execution between the system on the test and a test, right? So here, this would be the unknown model of the system on the test and the test in my proofs. They would be synchronizing on the alphabet of the system on the test. So whatever events the system on the test offers to its environment would be synchronized with the test that would be guiding that system. But we also have the idea that those events, the specification events, called here alpha ST, they are hidden, right? We have to do that in Csp to say, right, do I put two elements in parallel and they are communicating with each other via some events? In Csp, it means that if I am then a third party, an environment to that parallelism, I can see those communications happening and I can interfere. I could block a communication between the tester and the system on the test. And that's not what we want to do. So if that's not what I want to do, then I have to hide those communications, and therefore I need to have special events that give me my verdict. So here's to explain to you what these events are. They basically ink for inconclusive test, pass for a successful test, and fail for a test that revealed an error. And these special test events will have to be part of my test. They are the indication of what's actually going on, because the interaction between the test and the system on the test is private, okay? So, testing against traces refinement is the first that we studied, and basically what we note is that we need to test the system on the test against the traces that are not in the specification. I don't know how odd you guys find that is, because what we have to remember is that we're testing for traces refinement. It makes no sense for me to look at the model and look for traces of the model and ask if the system on the test has that trace, because it doesn't have to. According to trace refinement, it doesn't need to have every trace of the model. What it needs to do is every trace that it has, it needs to be a trace of the model. So what we need to do is to try and trick the system on the test to do something that it's not allowed. So what I need to look at is what are the traces that are not in my model, okay? So we look at the forbidden traces, and we see that we only need to look at the minimal prefix of these forbidden traces. For instance, for my example, we have that collected, is stored, and too far is forbidden. If you go back to the last time I wrote this example, we have collected, like happens at the beginning. Once stored happens, I need to go back to simple DTP, too far shouldn't happen. So that's a forbidden trace. So there is no point in my trying collected, stored, too far, and collected. There is no point, because once I've done that and I say, okay, collect, stored, and too far, if the system on the test done it, I already found a problem. If it hasn't done it, it's not done that, it's not going to do this one either. So I only need to look at the minimal traces. So we have a proof that the exhaustive test sets, or the test sets, the exhaustive, I think a terminology that's not universal in this community, it's Marie-Claude's terminology, the tests, the set of tests that is large enough and just enough to review all the errors. I will give a formal definition in a moment. The exhaustive test set is formed from tests from traces S of the model, followed by A as a forbidden continuation, an event that is not possible after SP has done S. Okay? So you pick S and you pick A and you construct a test from that, including the verdict events. So basically what you're trying to do, can I drive my system on the test to do the trace S? And if I can do that, can I then trick it to do A? So I go, here's an example, for instance, for collected and stored. Collected, once I've done collected and stored, can I trick it to do transferred? That's one test that I can write. And so I say, okay, at the first point, my test is inconclusive. Then I try to make the system to do collected. If it does, I say, okay, it's still inconclusive. I haven't got to the end of the trace that I'm trying to drive it through. Can it do stored? If it can do stored, I say, okay, I drove it all the way there. I will say pass. I'll give it a chance. But can I trick it to do transferred? If it does it, we say fail. If it never goes a fail, it will stop at pass, and that's my verdict. And so what's the notion of exhaustiveness? Is we say that SP is refined by SUT, here represented by its model, if and only if, for every test in that set, every trace does not finish with a fail. I never go as far with that system as the event fail. Okay? All right? So that's the tests for traces refinement. The tests now for failures refinement, we took advantage of one very important observation about failures refinement, which I think it's due to treatments, first of all. No? I think I found it in your paper. Right, I need to fix that in some paper that I wrote in that case. Anyway, so Marie-Claude brought this observation here, that failures refinement can be described as a conjunction between traces refinement and a notion of conformance. And that is an observation that I now need to tell Brinksman that has worked for even the more complex models of Csp, for refusal trace, for input-output refusal trace, for TikTok as well, including the notion of time. We can always decompose the notion of failures conformance with traces refinement, so every work that we do about testing from traces refinement is relevant in even the more complex theories, and some notion of conformance. And the notion of conformance ignores the issue of traces, but says, where I have a trace T that's both in the model and in the system on the test, the refusals of Q, which is the system on the test, after that trace T, the set of refusals are sets of events, so the sets of events, they are included in the sets of events for P after T. So there I am completely ignoring the trace, but for every trace that the system can have, the set of refusals can be, one is contained in the other. So that means that trace and conf can be checked separately, okay? And that observation means that now it's relevant to think about what's the exhaustive test set for conf. Now what we have to do is that we need to look about the traces of SP and traces of the model of the specification, try to drive the system through that trace, and in the end, we need to make sure that the system and the test cannot refuse all events in a set that's accepted by SP. So even though the model is based on refusals, the tests are based on a notion of minimal acceptances. And the observation that minimal acceptances are enough is important here. So the tests for conf are made from traces and sets of acceptances, where the sets of acceptances is minimal. And what happens is, for instance, if I have a test for S and A, S with events A1 to AN, I'm going to try and drive my system all the way to AN, And then I will say, okay, I am going to assume that you are failing, but you have a chance. Here's a set of events that you should accept. If you do accept it, then I'll say pass. Okay? So here's an example. Let me see. An example here, for instance, collect, stored, and after that, a minimal acceptance is collected. So here, after I've done collected, there and stored, a minimal acceptance is collected. So the minimal thing that I need to accept there is collected. So I do inc collected, inc stored, fail. Are you going to do collected? If it does, then it passes. Okay? So that is, and that's enough for me to consider the minimal acceptances. If I have that a set of events is an acceptance of a system, which means that the system must accept those events. If I put more events, it is still an acceptance of the system, but there is no point in trying more. But it needs to accept that minimum. So the extra test wouldn't add any information to the testing. And that's what I have proved, that for every test in that set, if I look at the failures of the execution, now I need to look at the failures, either the last trace is not fail, okay, or the failure is different from inc pass and fail. Either it's not fail or it hasn't terminated. It can proceed, it hasn't deadlocked yet. That's what means. The failure of the execution is not inc pass fail. It means that there are more verdict events to come. And if that's the case, then that is the case, that is a theorem that shows that the system is conformant. Okay? To finalize, and I think this is not relevant in this community, of course we are aware that we're running testing against systems, not process, and all these are theorems about Csp processes, and we need to realize all these results in terms of systems, and this is something that we are giving a rigorous account of it, not something in terms of semantics of Csp. So the main event that we have is that according to our testability hypothesis, the system under test passes the set of tests for trace refinement and for conf, if and only if the specification is fairly refined by the unknown Csp model of the SUT. And the notion of passing is that the SUT passes a test if for every SUT passes a test suite, if it passes every test. To pass a test, you need to carry out k experiments and observe no failure, and the verdict is a failure according to what I described there. The last event being a fail, and I have a deadlock. Okay? So that is the core theory of Csp. But more work was needed. First of all, these tests are very naive. I am surprised that you haven't complained at me yet. And I was just going to say patient, patient, patience, because of course we know that they can be factorized, they can be optimized, and we have done some work in that direction. Of course, those exhaustive test sets are infinite, they're not usable, we need to have finite choices over that. And we have therefore done some work on selection strategies based on data flow, coverage of synchronization, event coverage, mutation test. Event coverage is particularly interesting because, of course, for trace refinement, you try and say, here's a test that is going to cover such an event. But the system may not ever carry out that event, and that's not a failure. You're going to say, I passed that test, but it's because you didn't actually cover that event. You didn't go all the way, and not carrying out that trace is all right. But then, have you really covered that event? What kind of notion of coverage is that? So we needed to do some work to have some more sophisticated drivers that would try and actually cover an event, because there may be another path of the system that actually realizes that event. And if I want to cover it, I may need to consider to have a more intelligent selection of the traces. More interesting perhaps is the data-rich process algebra that I mentioned, circus, for which we described symbolic tests. Symbolic tests for traces, symbolic tests for conf as well. Here's a very simple example where we have a system that is data-rich, but interaction is via channels in and out that take some value, that carry some value. And the symbolic test here would say, okay, it's inconclusive event, but now I have a input event with a data alpha over which I have no restriction. Next, I have inc again, and now I have an output event, and that the communicated value beta has to be equal to alpha. Now going on, I have another input event where I have a gamma, no extra restriction, just alpha equal beta, but now I say pass, and I'm now going to trick it with an output that says, okay, I have a delta here, and now I have alpha is equal to beta and gamma is equal to delta, and then if that happens, I have fail. So that symbolic test is representing a collection of tests. We have a scheme to generate the symbolic tests and to instantiate the symbolic tests to generate concrete tests for a system, which would be based, of course, on SNMT solving. So if I chose 3 for alpha, it means that over there I had to choose a 3 as well. For gamma, I can do whatever I want, so I choose 1, then over there I have to do the 1, and so on. So the whole theory of how to generate these tests using concepts of the operational semantics of circus, data-rich operational semantics of circus, is defined to address this problem. Okay? So I'm conscious of time. I want to tell you at least about inputs and outputs. When we move to say in CSP, now we want to distinguish events that are inputs from events that are outputs, the vision that we take is outputs cannot be refused. So it makes no sense for us to record refusals where outputs are being refused. And so we change the semantics of the language, the failures in this case, to eliminate such refusals. And the tests for traces refinement do not change, but we have a similar notion of conf, but more efficient tests. I think it was a very pleasing observation for us, is that when the moment that you make this distinction between inputs and outputs, the sets of refusals there are fewer refusals. Well, what am I saying? They're infinite with infinite. If you take a finite subset, inside a finite subset, you reduce the size, okay? So you have, if you made your selection strategy according to some criteria, you get a smaller set, and so you get fewer tests. But then you observe that the denotational semantics that we obtain, it is isomorphic to the denotational semantics used in suspension traces, which I'm sure you will have heard of. Suspension traces includes a special event, delta there, to model quiescence. So quiescence are represented here by the fact that there is no non-determinism at that point. There is no output that is enabled. So here, for my example, I say collected and too far are inputs, but outputs are stored in transfer. I say at the beginning I have some quiescence, then I have collected. Collected goes me to that choice. That choice I have an output enabled, which is stored, so I have no quiescence. Then I have too far, and so on and so forth. So that was a nice result, but we got very upset with the fact that conformance is then incomparable to IOCO. And that for us that's not satisfactory at all, because it means that if I give a problem for my developer, here's a CSP model that you need to implement, and he uses input-output failures as the conformance relation, and then the tester comes and tries to test it using IOCO, it might say, well, your system is wrong, and they will look, but it is input-output failures refinement, but IOCO doesn't hold. And in fact, these two notions are incomparable. And the reason that this happens is as follows. Failures refinement only compares refusals at the end of the traces, but compares refusals, arbitrary refusals, any kind of refusals. Input-output in IOCO lets you consider failures along the way. You can have quiescence along the way of a trace. But quiescence is a particular form of refusal only. It's not any form of refusal. For this reason, these two models, the conformance relations are incomparable. Yeah? It makes sense? So our solution then was to say, okay, what we need to do is to use refusal traces. So the refusal traces model of CSP is our answer. We have got a fully worked theory for the refusal, testing theory for the refusal models, where in a refusal model, traces or refusal traces, they are sequences that alternate between events and refusals. And with the possibility of a special kind of refusal, which is the bullet here, that is going to record instability. So here in my simple model, I've gone to one slide too far. So in this simple model, I can have, for instance, that before any event happens, before collected happens, I have a refusal of stored to far and transfer. After collected happens, I have a refusal of collected and transferred, but stored and too far are there. So I have this trace, I have all the traces that are subsets of it. This example, I have stored, collected, transferred, and then too far happened. The refusal that I recorded in that particular example, there is just the bullet, just because it's subset closed and including the bullet at the end. The bullet is to say, I am not recording a refusal at this point, and indeed, if you have a divergence, you cannot record a refusal, you can only record refusal if the system is unstable. And bullet is very useful because if I have refusal traces with inputs and outputs, I have to have a way of saying, after collected, I have an output, so the system is not stable. What is the refusal that I can record? The only thing I can record about it is the bullet, with the idea again that if I have inputs and outputs can never be refused. So the testing theory for refusal traces, again, as I said, very pleased in the separation between trace and refinement and conf remains. The refusals, however, are now given by traces. I want to know about refusals after a sequence of traces. And in this case, because I will need to pass from event, refusal, and so on, I need to change my notion of execution to give priority to the specification events. So I will look at an example here. What I am trying to do, like in the trace refinement, I am trying to say, I want to trick my system with invalid traces. So here's an invalid trace of my system, a test for just the first refusal set, and the test is like this. I say, okay, I put in choice, collect, stored, and transfer with fail. If fail will only happen if none of these events are accepted by the system. So these events have priority over fail. If the system accepts, then it goes to pass, otherwise it is going to fail. Okay? So see that the notion of priority needs to be used in this theory. Now, I'm getting to the end, and I just want to go back and so what about all these CSP and robots? What are we doing? What we could say right now is to say, all right, I generate automatically using Robo2 CSP models of RoboChart. I can use every tool that we developed for testing from CSP and apply to RoboChart. But it's interesting to look at mutation in RoboChart. Can I capture faults or typical faults of my system based on the model in RoboChart rather than trying to apply mutation in Circus, for instance, which is a result that we have. So we have done very technological work, but very pleasing result using a tool called Wodo that's been developed by colleagues in the University of Madrid. And that tool generates mutants for any language for which you can provide a meta model described in eCore with validation rules described in OCL. So we are using Wodo together with a eCore description of RoboChart and an OCL description of our validation rules. And Wodo accepts a RoboChart model in XMI. That model can actually be generated by Robo2. The reason why that arrow is in that direction, I'll show you in a minute. But using Wodo, we can give it a RoboChart model, the RoboChart meta model, and a Wodo program that describes mutations. We then obtain from Wodo a set of mutants. With the original model and the sets of mutants, Robo2 can provide us with CSP models for the original model and the mutants, and then we can use FDR to generate either counterexample, and that's a good, because counterexample in FDR, counterexample for trace refinement, for instance, will be a trace of the mutant that's not a trace of the system. A trace that's not of the system is exactly a trace that I need to generate my test. And even better, FDR gives me the minimal counterexamples. It's exactly the trace that I need in the exhaustive test set for CSP. So it's very, very nice and neat. Or we have that it passes. If it passes, that's not very good because it means that my mutant is a refinement of the original model, so it's not interesting. So mutations are specified in a very high level in terms of mutation operators. Waldo applies those operators at random according to various selection techniques. We can write something very general. Because of time, I'll just show you this one. We can just say modify target, and we say target is here is an element of the RoboChart meta model. It's a target from one transition, which is another element of the RoboChart meta model, to another state. So this is the kind of language that we can use to program mutations in Waldo. And using that, we can use Robo2. It has now a plugin for testing to compare the original model to mutants. It accepts the mutants, it runs FDR, and it then generates the counterexamples, a full report with all the counterexamples. And so I think, yeah, I have time for one example. So here's my DTP machine from the beginning, where I was showing the Foraging Robot. This is this original state machine. If I have a mutant that instead of starting the behavior in exploring and goes directly to go to nest, I then get a counterexample that says, well, there is a trace that the mutant can do, which is to start setting the distance to 0 before it's actually collected something. It goes directly there. So that is a counterexample, and I can use that as a test. But it's not all good news, because here's another mutant, and I think this mutant is because, let me see if I can remember, it can, this transition here, go to source, that should go, from go to source, once it's collected, goes to nest, and that will try to go to nest via a walk over there. The mutation is that it goes directly to the state where it's going to the next directly without considering the distance and so on and so forth. With that, I generate a mutation. I generate a trace that is a counterexample, but this trace is not very useful, and I'll show you why it's not. Because it's showing here that if I collect an object, I set the distance to 0, and then I have it stored immediately. That is not realistic. That is only happening if I can collect the object and store it where I found it. That is not an environment that is reasonable for this application. So what we need to do is to make a model of the environment. So at the level of RoboChart, we are creating a language that allows you to describe assumptions about the environment. Because I need, in the environment, a model of the robot, a model of locations, and we're using those models of robots and model of locations to establish how the operations and the service of the robotic platform are related to environment conditions via mapping, and using this, then together with the software model, get rid of irrelevant tests. That's the work that we're doing, and we need to do to understand what is the kind of CSP model that I need, how can my roboticists write those models in a way that's accessible to them. And we are starting at the level of the simulation, because what the roboticists do is that they write the simulations. So we are creating a language for them to write the simulations in a way that's better than C++, and then we will write the mappings coming from simulation back to RoboChart to achieve this goal. Okay? So that's what we're doing at the moment, and I think CSP and the testing theory is extremely interesting to help us with this work. It's been fascinating. What's next is support environment modeling, comprehensive set of mutation operators we are developing now with extensive experiments, take into account of our TikTok theory. The testing theory is under development. But what is distinctive about the work of RoboStar? Notations, I don't want to ask anybody to be writing CSP models, especially the ones that are timed, probabilistic, and hybrid. No. Notations though, that are akin to those that are already used. Sound integration, full life cycle, including that of testing. Thank you so much for the opportunity to tell you about all this. I hope you liked the area and you're excited about robotics as I am. If you are, come in November to a lovely event that we are organized in London, the Royal Academy of Engineering, where colleagues from all over the world will come to talk about their work in this area. There is quite a lot of people that are picking the challenge of